Hey guys, Mr. Milton here. Today we're going to look at bisectors and triangles notes. At the end of this video, you should be able to find the missing side lengths and draw conclusions using perpendicular bisector and angle bisector theorems. And you should be able to explain how to find the missing side lengths. All right, so vocabulary note, perpendicular bisector has two parts. Perpendicular, that means that the lines that intersect at a 90-degree angle. And bisector means a line or segment or ray that cuts a segment in half. So therefore, a perpendicular bisector is any line or ray that cuts a segment in half and meets at a 90-degree angle. Okay. An angle bisector is a segment, line, or ray that cuts an angle in half. Okay, so bisector, 2 into 2, perpendicular. We've seen that enough, I think, 90 degrees. All right, so perpendicular bisector theorem says if a point is on the perpendicular bisector of a segment, then that point is equidistant from the endpoints of the segment. Okay, and that means equal distance. So let's go through the proof of why this is true. Okay, so I'm going to do a two-column proof. Okay, statement, reason. And again, our chapter and lesson won't necessarily be you using this a lot, but I want to establish why this is true. So they said given that CD is the perpendicular bisector of AB, and they want us to prove that CA is congruent to CB. Because if we do prove that CA is congruent to CB, we're proving that any point on this perpendicular bisector will be equidistant from the endpoints of the line it bisects. Okay, so one, I'm going to start with the given. CD is the perpendicular bisector of AB. And that's given. Okay, so I'm going to write that down, and then I'm going to mark it. Boop, boop, boop. Okay, so these are a couple things that I know. I'm going to name this point D so I can talk about it. Okay, so number 2. Now I can say that AD is congruent to BD, because that's the definition of bisector, right? And I'm going to say that angle ADC and angle BDC are right angles, okay? Definition of perpendicular, and then I'm going to say that ADC is congruent to angle BDC. Okay, definition of right angles. All right. Whew. All right, so all that from the given. Got a lot. All right, the next step now that we can say is that CD must be congruent to CD. And we know that because of the reflexive property. Okay, and so CD is congruent to CD. As you look, you should see, hey, we have side, angle, side. And so I can say that triangle ADC is congruent to triangle BDC because of side, angle, side. And if you guys remember the triangle proof chapter any, then maybe at the beginning of this problem, you're like, hey, I'm trying to prove that two sides are congruent to each other. Probably going to use CP-CTC, and we did. So now I can say that CA is congruent to CB because of CP-CTC. All right, so we got to prove that CA had to be congruent to CB. Now here's the nice thing and why it's important. No matter where we put C on this line, if it was here or here or here or here, anything on the perpendicular bisector would make this true because side, angle, and the reflexive property would give us a different side. Okay, and that really drives home the point that a perpendicular bisector, if a point's on a perpendicular bisector, it's going to be equidistant from the endpoints of the line it bisects, or the segment it bisects. All right, so with that, let's go on to a point, or next problem. It says, which segment is the one getting cut in half? So as we look at this next problem, because it's important for us to understand which segment is getting cut in half so we know on which line has to be equidistant from the endpoints. So as we look, CD, we have hashes that say, hey, this segment is congruent to that segment. So CD is the one being cut in half. Which segment is the perpendicular bisector? BA is the line that actually is the perpendicular bisector. So with that knowledge now, AD, let's see, since this is on the segment that's bisected, this is 4, it must be equidistant here, that must be 4 as well. So AD is 4. BC, as we look, okay, our perpendicular bisector here has to be equidistant from the points that it bisects. So it's 5 from D, and from the line that bisects the other side is 5. Okay, pretty straightforward. All right, converse of the perpendicular bisector theorem says if a point is equidistant from the endpoints of a segment, then the point is on the perpendicular bisector of the segment. Perpendicular bisector of the segment. So, and that's just saying if we find out later that a point is equidistant, then that must be on the perpendicular bisector. All right, here's an example. It says find the value of x and explain how you got it. So, as we look, oops, should be here. Sorry guys about that line. All right, so what we notice is, hey, FH, F is 9 away from H and 9 away from G, okay, that distance. And so what we know about this line then is it must be the perpendicular bisector, okay? And that helps because it makes a 90-degree angle, but helps us solve this problem because now we know that 5x, this segment, must be congruent to x plus 5, this segment. 5x minus 3, sorry, it's congruent to x plus 5. And so 4x equals 8, x then must be 2. Okay, I spoke the explanation out, right? Fe must be the perpendicular bisector. Perpendicular bisector of HG. All right, because it's equidistant from, I say it's because F is equidistant from G and H. Remember that when we talk about the distance, the length of the perpendicular segment from the point to the line. Perpendicular. Okay, when we're saying distance, we're always talking about a straight line, right? And so perpendicular helps us to make sure that we know that we're talking about straight distance, not like a curvy distance. And that's the length that we're talking about, or the distance we're talking about. Angle bisector theorem, it says if a point is on the bisector of an angle, then this point is equidistant to the sides of the angle. Equidistant. Again, when we talk about distance, we're talking about 90 degrees. So in this diagram here, it says name the angle bisector. So what we do to figure that out, or to identify that, is we look and we say, okay, this angle is being bisected. We can tell because they're congruent to each other. And so we have CF is the line that splits that angle. And so CF must be the angle bisector. We call it ray, or you can call it line. I'm just going to call it line in this case. How do we know it's the angle bisector? Well, because we have BCF and DCF are congruent. And since F is on the bisector of angle BCD, and F is equidistant to, we're talking about CD and CB. All right, so we know that these two then must be congruent to each other. That's that distance we're talking about. So here we can find that out and solve it and say, okay, that must mean that 5x equals 2x plus 24. 3x equals 24, x equals 8. And FD then, Find that out. 2 times 8 is 16, plus 24 is 40. Okay? And you could be able to plug it back in and make sure that you got your right value for x. 5 times 8 is 40, so BF would be 40 as well. The converse of the angle bisector theorem says if a point on the interior of the angle, there we go, is equidistant from the sides of an angle, then the point is on the angle bisector. Okay? Basically the same thing as if we find out that it's equidistant from the sides, then we can tell you that it's on the angle bisector. If we know it's on the angle bisector, then we can say it's equidistant from the sides. Okay, so those are converses of each other. Okay, so how far from K is ED? We look, we have K here, ED. We're trying to find that distance. Well, as we look, we can see, as we extend this, they're telling us that this is 10, right? And we can say 2 hashes tells us that must be 10. Well, 2 hashes here tells us that it must be 10. K is 10 units from ED. Since K is equidistant from EH and ED, the two sides of our angle, right? K is on the angle bisector of DEH. So now they're asking us to find X. Well, we can find X because angle bisector indicates that these two angles must be the same. 2x equals x plus 20. Subtract x, x equals 20. And so DEH, making sure that we understand that they're asking us for DEH, that's this whole angle. This is 40, this is 40. DEH is 40 plus 40, which is 80 degrees, or 80. All right, so that's the angle bisector theorem and the perpendicular bisector theorem. Okay, and their converses. You can use those to solve for missing angles and measurements now. See ya.